predictor card. Say we have 228 predictors, and at a time we can take only 5 predictors, 5 random predictors, just 5. But this is tuning parameter. You can find what's the best number, and then you do it. You can try 10, you can try 20. You do it many times, like thousands or 2,000. Random forest usually takes a lot of time, so it's a serious model. But surprisingly, it does show you good results. So what does it mean? If you think, what does it mean to take a small number of random predictors, right? So sometimes you take these good predictors meaning the predictors that are very well for the models and can be very well, the value we would like to predict can be very well predicted with just the small set of numbers. Just occasionally or randomly we found them, and they would be multiplied in the model. And then we took, say, 5 random predictors that are not really good for the predictors. And then, but because of the big number of iterations, we will always, kind of come out with the best choices. Even on a weak predictors, we call predictors that are good for the model strong predictors, and we call predictors that are bad for the model weak predictors. Even weak predictors can be, used in a smart way, and this is why random forest is very simple. The algorithm say is like this: we select the number of models to build. So it means how many integration m, the same m as we used in embedding. And again, you see we generated this trap sample of the original data. But then, it's not bootstrap sample on the predictors, it's bootstrap sample on the original data. We do bootstrap now not on predictors, but on all our data. So now we're not only playing with the randomly selected predictor, it's this block. Randomly select k less than p number of the original predictor, and select the best predictors among the hard predictors to partition the data. But we also kind of shuffle the data, our original data. This is where another randomness comes. Bootstrap sample from the data would generate not exactly the same samples each time the model runs. That's it. So this is what is random forest is about. And now we come back to the workshop. We come back to the workshop and try to run the model. Hopefully it works for everybody today. Random forest. So what we do, okay. You see, I didn't use the number of 3,000, the same with the neural network. Unfortunately, we try only a small number of 3 because it does take time. Maybe, well, 5, maybe your computer will run and use 100, I don't know. But still, to be sure, we're now just playing with models. You don't need to get a good performance. You're just learning how to use this model. The only difficult thing is to type this data frame, which is, maybe somebody would explain what is the, you see, there is a function created from number of columns, from our trained data. Could possibly somebody tell what would be this function mean? Floor, sec, 10, number of columns, length 10. So we create some kind of tuning parameters. Weight is always the tuning parameter, and try to guess what kind of numbers we are choosing by this syntaxes. Number of columns, every 10.
and then 4 to make it and so we get 7 options.
Exactly. Exactly. Yeah, so set from sequence. So we take a sequence starting from the number of 10. This is number of random. That would be tuning parameters, tune grid. Tune grid is about tuning parameters. That's where the method RF means random forest. And we'll try different numbers of tuning grid is always different number of trees, different number of random predictors. And different number of predictors, we do it this way. So we took the sequence. You can actually, to see what are this number, you can independently execute this just small number. Set from 10 to number of column length equal 10 and see what are the numbers are generated. What are the outputs? You can always, when you don't understand how does it work, you can split it in the simple blocks, run it in the simple blocks, and then see what are these numbers. Importance 2, we would like to extract predicted importance. So it takes time. That's why you have it here as a parameter, because you can either use it or do not use it. So here is importance is true.
This model is better than all previous ones.
Even with 5 trees?
With 5 trees.
Even with 5 trees. So 5 trees runs immediately for you?
Yes. Almost immediately.
Yeah, it took like 10 or 20 seconds.
3 seconds.
Okay. Then you can try 100.
Okay, 500.
Try 100.
It should take a couple of minutes.
Yeah, while we're waiting for it. But something is, yeah, it's why is it that? No, yeah, it's worked. Now we can do prediction. Well, first see what happens, and then you can close it. You can always close the model. So actually, you can see now tuning parameters. When you output the model tune, you can see tuning parameters. And tuning parameters are exactly what we created. It is a sequence of 10, a number of columns 228. It goes 10, 20, 30, right? Or less. It's created 10, less than 10. So it's splitted all the numbers in the divided by 10, it goes 10, 34, 58, and now this means how you can actually do tuning parameters one by one. If you have time, you can, and if you really want good performance, you can try go stepwise by one. So you can try 5, 6, 7, 9, etc. up to 228. If you have time, and find what are the best number of random predictors to include into the random forest. So what are your best number? What is the best tuning parameters? So finally you got something like this, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the whole set was exactly divided into 10 values. That was the function. This is our tuning parameters. And tuning parameters is a number of predictors to be included in a tree. So first we randomly take 10. This is actually irrelevant because you just have 228 and every time you randomly take all predictors, right? It doesn't make sense to include this one. But the only randomly here, the randomness will come from the bootstrap sampling because we're not only randomly taking predictors, we also, when we train the tree, we do bootstrap samples from the data. That's why the result can be different for everybody. It's not exactly the same, but here is actually my result is that 228, so taking all predictors finally into the random forest is the best choice. What do you have? What do you have?
So this 100 trees is dot 90 and dot
okay, that's
66 on LC, dot 66 on C and dot 90 on S squared. This 100 trees.
I'm still waiting for my random
good. I think I run it just on 5, maybe on 1,000. I'm not sure already how did I run it on 5 or on 1,000. I don't remember yet. So of course it depends. So usual practice, it's 2,000 random trees. So 2,000, 1,000 is not enough. 2,000 is a good choice. 2,000 is a good choice. Which is a good choice. Okay, then yes, you can. This is if you plot your model. You see, in my case, somehow the RMSE always goes down till the end. You will be having different plots because you said it's not the. But this is also, it depends how many trees you run, that's for sure. And then, again, well, I assume you can do the plot here. This is what the most you get with the local, so it's not all the predictor but the previous value, not. Okay, this is what is random forest is about. And because we included this parameter importance is true, we can also use a random forest. We can use the importance, variable importance parameter. So I know usually actually you build the model, for example, if you want to build a good model and you use, say, support vector machine, so far is the best. That's why I remember even for this data. Support vector machine is if you before the gradient boosting, would be the best result, would be the best model. But then for choice of variable importance, random forest is number 1. It's kind of reliable, so you can use random forest algorithm just to generate, not to build a model, but to generate variable importance. At least many people do it. For example, using SVM or gradient boosting and then do variable importance just on random forest. And you can scale false and have somehow absolute maybe values, weight value, or if you do scale true, you get 100%, and then the values go down to a certain extent. Okay, we are moving good. Actually, the only one algorithm is left studying. This is all called ensemble models. Ensemble models meaning you take not just one tree, one decision tree, but all together, and they vote like democracy. All the trees are votes for the best solution, and the results are accepted according to the democratic vote. Does this work for everybody who needs help before we proceed to the next algorithm? So level C download packages, some is provided by should be somewhere. If you move it, if you don't know where to move, if you move the download packages from directory, you can see, for example, you can if you find where it is, then maybe you can just copy there and then put it automatically. You should go to the studio, not like this, but this way not like go to our studio, hold in the application and see where it's at. Do you secure it or apply predictive modeling package there? Okay, boosting. Boosting, let me tell you a few words about theory. What is boosting? Now we do boosting. Boosting again is not necessarily on trees. It's not necessarily on trees. It could be on any algorithm. This is for random forest. Again, solubility on random forest. This is a comparison. Randomly selected predictor. The plot you already actually had this plot or similar wise. This is we don't need this kind of detail. This is very important. Boosting. Boosting again. It could be we now starting boost on trees. And the algorithm we study will be called other boost. The main idea that I already told you, have a weak classifier, number of the weak classifier that say predict marginally better than random, right? So you can, and you can combine them or boost it, this weak classifier. Combine them or boost it like promote, to produce an ensemble classifier with superior misclassification rate. Let me, so the algorithm that we started called adder boosting, adder from adaptive, and I would like you to show a movie that explains it, to my opinion, very nicely, and you will have the notions to look at later at your own convenience. Maybe if you don't hear the sound, that's fine. Of course, you can see. I will comment. It's only two.
Learners are focusing on areas where the system is not performing well. One of the most well-known algorithms.
So we actually focus on the data that are not performing well.
Here's how AdaBoost works.
So you see, this is our data split in a train and a set. That's what we usually do. We randomly select.
This is something different.
We randomly.
And use it to test the model.
Here is. You see it.
That some of the points in here.
What happens? So what's in the course? Okay, you see what happens? So we just randomly selected the same as with random forest. We selected some data randomly, not necessarily all predictors in all the data. We just train the model and there is a model. And then we test this model on the same train set. So the original train is larger than what we did for the model. And once we did it, some data would produce large errors, right? Because we test and say how we predict. Some data will be well predicted, some data will produce bad results. And we specifically mark these
Are not well predicted.
are not well predicted. So, for example, these points that he draws with the red dots.
When we go to build our next pattern,
And then
we choose randomly from our original data. But each instance is weighted according to this error. So these points that have significant error are more likely to get hit.
so once we create the second iteration, we weight this model. So we randomly take, but we say let us took more often this error reports to be included. We would like to train our model on this error. So the way we do this random sampling is now weighted. We put more weights on this red dot that produced more error on the same model. You see? So we selected actually erroneous points for the second.
And any other individual instance.
So now you see the next collection will include not all, but say majority of the points
And we tested
that's
our
created
system.
error. Then again,
We have a sort of miniature ensemble here.
we test our model on the set. Again, we take all the train to test the model.
Combine their outputs. And again, we measure error across all the
Or we combine, we even combine, no, we don't, so we combine the model, we have an output, and then we train, and we get new errors. So now this point produce more errors.
over and over again.
And then we do it many times.
So to recap, bagging with the build
That's what bagging is.
is simply choosing some subset of the data at random with replacement. We produce bag in the same way. Boosting is an add-on to this idea where in subsequent banks we choose those data instances that have been modeled poorly in the overall system before.
Let me just show. Let me show you again without the words. So for you, so bagging is just you bootstrapping.
Very simple variation on bagging that strives to improve the learners by focusing on areas where the system is not performing well.
Okay. Okay.
First thing is a fairly simple variation on bagging that strives to improve the learners by focusing on areas where the system is not performing well. One of the most well-known algorithms in this area is called ADA boost, and I believe it's ADA, not ADA, because ADA stands for adaptive. Here's how ADA boost works. To build our first bag of data, we select from the training data, and train a model. The next thing we do, and this is something different, we take all of our training data and use it to test the model. And we're going to discover that some of the points in here, our x's and our y's, are not well predicted. So there's going to be some points in here for which there is significant error. Now, when we go to build our next bag of data, again we choose random algorithm, but each instance is weighted according to this error. So these points that have significant error are more likely to get hit when you go into this bag than any other individual instance. So as you see, we ended up with a few of those points in here, and a smattering of other ones as well. We build a model from this data, and then we test it. And we test our system altogether. In other words, we've got a sort of miniature ensemble here of just two learners. So we test both of them. We test them by inputting, again, this in-sample data. We test on each instance, and we combine their outputs. And again, we measure error across all this data. Maybe this time, these points got modeled better, but with some other ones up here.
So gradient boosting is actually the variation how you select points. So here is after boosting, you just put, you randomly put ways to select the errors more randomly than the normal points.
Boosting is an add-on to this idea where in subsequent bags we choose those data instances that have been modeled for the overall system.
Okay, this is what it is boosting, and let's see now, actually now when I'm on this page list of modules available in the current package, again, if I try to search here boost, you can see you have boosted classifications trees. But again, boosting, as you see, boosting can be done the same as bagging. Bagging and boosting can be done on any type of model, not necessarily tree. Here, boosted generalized additive model, boosted generalized linear model. So you can combine linear models, not necessarily just boosted linear model. Boosted logistic regression, we didn't study it. Logistic regression is for classification. Boosted smoothing splines, it's variation on mass. Boosted tree, of course. And I guess that's it. Boost. Okay, so the extreme gradient boosting, the same gradient boosting is here. So maybe if we have an extra time, as for classification, XG boost. boosting, because you see many tuning parameters. So let me stay here. Maybe we can come back to this model. So the summary of the boosting, let us see what is the algorithm. The algorithm, we select the 3 depths. So the 3 depths would be the tuning parameters. And it's gradient boosting already. No. Let's try first other boosting. Okay, we'll come back to the other boosting. Go to workshop, and see what kind of package do we need to run other boosting. Here it is. Here are gradient boosting methods. It's actually not really the other boosting. It's gradient boosting. Already, okay. Let's run it. Gradient boosting. So that's let me come back to the algorithm, because if it's gradient boosting, we should see the algorithm to understand the tuning parameters. So the tuning parameters are: you select the 3 depths. You select the 3 depths and the number of iterations. And yes, you compute the average response. Average response, you remember, we cannot predict the exact value. We predict something very, some average or median value. Then compute the residual. Residual is an error, right? Difference between observed value and the current predicted value for each sample. For regression tree of depth J, using the residual as the response. And then the same, we update the predicted value of each sample, adding the previous iteration to the predicted value generated in the previous step. So we kind of look at the error. We look at the value that was produced. It does not say though how you create the next sample. But now this is a variation. It's not exactly as a boost, adaptive regression boost. It's a gradient boost when you go gradient, like you go towards the in decreasing the error. You update the predicted value of a sample by adding the previous iteration predicted value to the predicted value generated in the previous step. That's why it's called gradient boosting. This is actually the very powerful this is a very powerful method, and as I told at the beginning, majority of the cargo competitions won till recently, maybe even till now. I didn't follow up for some time. One with the gradient boosting. There are variations like extreme gradient boosting. It's also available in the package train. So let's try and see how it works in real life. So now we have too many tuning parameters. Actually, if you have this chapters folder, you probably can copy this piece of code from the chapters. Or alternatively, you can find. I don't think we are able to run all this code in the class. It's too much. You see, we have 3 rows of tuning parameters. First, interaction depth of the tree, which is sequence from 1 to 7 goes by 2. So you took 1, 3, 5, 7. Just 4 values. Then sequence number of trees, sequence from 100 to 1000, approach by 50, meaning it will be 100, 150, 200, 250, 300, 350, etc. Then you have shrinkage. Shrinkage is actually this gradient. How do you approach narrow? The same shrinking as you can compare it to the learning rate in neural networks. This is kind of that meaning this parameter has. And Berger, suppose you can actually try Berger's true, and then you see that once you run in the model, you will get a lot of output.
Да, min-ops and not. Здесь. Looks like we need one more parameter in order to run this method. It requires to specify n min-ops and not parameter, and I'm not sure which value should be specified here.
If we should have column number of tree interaction, number of min of this node. Maybe it's update of the package in a new version. Probably it's something with, well, let's add it.
Okay, and which value should be specified?
Let's specify, try one.
Okay, let's try.
Let's try.
Yeah, it's like
So does everybody have their own tuning grid? It's maybe the new version of package that it requires an additional parameter. So then add this additional number of minimum observation in the nodes. Let's put it one. Add it to tuning grid.
I said min F's, min ops in there.
Yeah, just put it one and see what happens. It's a new thing, so then because I have the slides from the previous year, they updated the package and updated the number of tuning parameters. But I don't think it will finish in reasonable time. That's the problem. So you have to stop and try it on I don't know, on some fixed number. So you want to, if you run it, I'm afraid it won't finish by tomorrow morning. So you see it works. Let's try it with some fixed number of parameters.
min-ops and not. Reverse решение. Напиши просто равно единице. Не так просто равно единице.
Короче, модель еще точнее, чем все выше. Почему я это сделал?
У меня на случайном листу, кстати, на тестовой выборке получилось там довольно большой РМСЕ. получится. По-моему, SVM был лучше. По-моему, SVM у нас был лучше.
Я хочу чуть-чуть параметров решили, это станет лучше.
Ладно.
И то по RMC уже лучше, чем на 5000.
Окей, подкручивать на 666. То, что со слайдом. Да.
So, who managed to run it with some set of parameters? Huh?
Well, it's still running on my...
No, with the whole set it will run smoothly.
Okay,
You
so...
have to reduce, take one, just replace the grid and put just one parameter, say
Let's say...
maximum, whatever you like.
Okay.
The small, because you will never, no, guys, it will never finish by, with all this tuning grid. We have to try it with just one parameters, one interaction depth, number of trees, something like, I don't know, 100 or even 100. Shrink it, let's use shrink it like 0.1, or you can try both, or you can try either or. So who managed to finish the model?
I was able to finish the model, but for me it shows a huge value of RMSE and quite low value of R squared.
Yeah, because it's what kind of, you just randomly choose parameters. Yeah, well, it doesn't matter really the parameters here because we don't know what has best on board. Oh, come on.
The one was 200.
Oh, nice. Oh, you should share your results. Which one is it? You run all the grid. Ah, so not that bad. Actually, the whole grid was run. Maybe I was.
But not after 1000, it's just 200.
From 100 to 200.
Up to 200. Step by step.
You even run everything. Oh. And you see the result is to, no. R square is 90% here, so then now it's like randomized square.
То есть последняя модель, которая не вот это.
And then, so what should the guys do? Even the rest is it's overrun as that's why it's the best. R squared 90%. Yeah, I don't remember what is the SVM. But maybe interaction depth 7. Okay, we can get you a hint. Try number of trees to 100, interaction depth 7. Try interaction depth 7, number of trees to 100, and shrinkage 0.1, right? Try this combination, because with this combination, we got just perfect results. R square 90%, RMSC almost 0.60. 7. And number of 100. And shrinkage 0.5. Just for 100. And 0.1. Try interaction depth 7, number of trees to 100, and shrink at 0.1. And see if we get the same excellent results, almost as SVM. Just one great result here. C is great in action. No, I think
Ну, вообще, можно включить эту штуку для параллельного.
Is it true?
Yeah.
So what are the
Теперь он
then?
не видит параллельно.
If you bring to this model, well, on train set, on train set, why am I seeing it for, no? Is that? Online one, so the same good result. Who have, you have this graphic first here, can you remind us what is?
Actually, yes, but I was recording every time not the results from the model, but from the test data. How the
Yeah, I understand.
Yes. So, just a moment. So I record on the RMSE, it was 0.6. And here for test set, it's like 3.88 RMSE. Yes. Well, here I'm trying to predict the values, and here it is.
Oh, it's open.
Yes.
By your model. No,
Yeah.
Okay. You did not run with the 7 to 100 Try 7.
7 or 5?
Try
Okay.
7.
Okay. Okay.
7 to 100.
And everything else.
Try it.
Okay. Let's try it. One moment.
Yeah, I think actually,
Я там все цифры там.
more research. Can you, because I forgot my list, can you write down your name and password and the date?
Actually, even with these parameters, it still shows well the bad RMSE really bad.
Strange. So who has good results and who has bad results? So we are not consistent actually. Interesting has the same results as you. So who has good result? Let's see. It's some randomness in the results. By good results, I mean like 90% R square and 0.6 RMSE. Bad results is like 4 point something RMSE and around random R square. Random means like 40%, 50%. Who has
Well, I have the results for the models and
for
for
the
the train
model,
set,
even for the model, even for
but
the
not for
model.
but not for the test set.
Вообще параллельно включать.
please raise the hands for the good results. With the 7, 1, 2, 3, 4. Good meaning 90%. Who has bad results with the same? Same parameter, I mean 7, right? Interaction depth 7, number of trees 200, shrinkage 0.1, right? No? On training.
I have a completely reverse results, really good results on the train set, but awful on test set. Looks like. But we are using the exact same parameters, it shouldn't be that way.
Okay, some history is going on, we have to find it out. But this is a tricky model, that's why you have this complicated tuning grid. And unfortunately, with this one tuning parameters, we cannot judge what is the best, maybe. So the model should be trained. Here we got the model trained, iterating through several options and finding the best parameter. Why is it why is it split so that actually for some it does work, for some it doesn't? I have no idea. Maybe this different version of packages too, actually. If it's installed right now, maybe the different version of R, different version of packages. Okay, so now you know how to run gradient boosting, and actually you can run if you want, but we won't do it in the class, extreme gradient boosting. So, but you see, when you look at the extreme gradient boosting, this is a number of tuning parameters you have to provide. So this is a lot of extreme gradient boosting. Though there are different variations. Here is extreme gradient boosting XGB linear, and then extreme gradient boosting XGB dot. And these are list of tuning parameters that should be specified. So these are number of boosting iteration, okay, maximum tree depth, okay, shrinkage also, you know. This is also loss reduction function, some sample percentage, some conceptual rational. So it's, that's why it took a lot of time to train the model and see what is the best parameter. But it's just a matter of time to set this tuning grid similar to what we did in a class for 4 parameter. Doesn't make it too much complicated to run it with this, say, 10 parameter or 9 parameter. It doesn't matter. It just takes time. Or you can run it overnight and see what happens. I don't think we should study qubits now. It's, I think, too much. There is a variation of qubits. But this is real addition. It's not an ensemble method. It's in that popular. So, okay, to summarize, we learned today simple regression, 1 regression tree, and learned to study your data by just looking at one single tree. It's very useful for interpretation. Then we study ensemble method. Ensemble method started with the bagging. Bagging is just bootstrap, so you build trees by bootstrapping your data, that's all. Aggregation of bootstrap sample, this is what is bagging. Then we tried random forest, and then we tried gradient boosting. I think that's it for the trees. Unless you have questions, you are free. Did you all write down your names? Because I forgot my piece of paper. You do.
Well, actually, I found out the mistake on my code. I used the salt test X instead of salt test expense. And it produced
the same.
No, that produced significantly worse results. when using
Significantly more sad.
yeah, and when using the solid-state strength, it produces the exact same result as anything else. So
So these are good. So now I want